Okay, so I'm going to talk about some early and some recent results on tidal disruption events and X-rays and in reprocessed optical emission lines. So tidal disruption was first predicted based on theoretical considerations in the 1970s. Then in the 1980s, a major question in extragalactic astrophysics was whether there is a supermassive black hole at the center of every galaxy. And it was Martin Rees who suggested and advertised the idea to use the distinctive manifestation of tidal disruption events in form of the luminous accretion flares to search for the presence of these supermassive black holes at the cores of quiescent galaxies. And he predicted these events to look like luminous EUV to soft X-ray flares with quasar-type luminosities, but from the centers of otherwise quiescent galaxies who in principle easily identifiable. And an early experiment which was well suited to search for these events was the soft X-ray mission ROSAT, which in particular in the early 90s carried out an all-sky survey in soft X-rays. So a number of events were detected with ROSAT, and let me just briefly summarize or show you the properties of two of these events which actually matched very well the key predictions, the order of magnitude predictions from tidal disruption theory at that time. So here you see one of the X-ray light curves of one of these events. Bright during the ROSAT all-sky survey, then it faded away strongly. This first observation, these first observations were covered by about a week, and the source showed a rise to an observed high state. At low state, deep Chandra follow-up observations were carried out, and you see that most of the X-rays now come from extended emission from the host galaxy. At maximum, from the very center, there's still 3 photons left, which could be linked to any nuclear emission, implying a very high amplitude of variability. Now, this is how the host galaxy of this event looks like. It's a giant barred spiral galaxy at redshift 0.01. So it's the second nearest TDE. The nearest one had been identified in X-rays later. And its optical spectrum is that of an H2 type galaxy with emission lines but no strong AGN continuum. However, in the very core, there is some excess O3 emission, faint O3 emission, which might have been excited by the flare and which was seen with HST. The second event is this one, XJ1242, which again faded away strongly and is no longer detected in the deepest X-ray follow-up observations with Chandra. This arises from the core of a galaxy, from the central region of a galaxy in interacting system. And here you can see the host spectrum. This galaxy is a completely quiescent, inactive galaxy with no emission lines detected at all, neither in ground-based spectra nor in sensitive follow-up HST observations. The decline of the light curve is consistent with a t to the minus 5/3 as predicted at that time by Martin Rees, and with some evidence for a drop before the early phase decline law at late times after about 10 years. So here's some numbers. The peak, the bolometric peak luminosity was quite high, in this case larger than about 10 to the 45 ergs per second. The drop in luminosity was huge, larger than a factor 1,500. And these X-rays come are consistent with rising from the core region and rise from the inactive galaxy. Now these observations very nicely match the order of magnitude predictions by Martin Rees at that time, who predicted, the key expectations are we should see a luminous flare which declines with a sharp rise. We didn't have tight constraints on the rise phase, but then a decline on the timescale of months to years, possibly following this law. He also predicted a late time drop beyond this early decline law when the equation changes to a different mode. And of course, they should arise in most of the cases from the very centers of quiescent inactive host galaxies. A simple black body estimation of the expected spectrum between the tidal radius and 3RS gives temperatures like this, which peak in the EUV to soft X-rays, again very well consistent with the temperatures initially seen. There was no prediction for the X-ray spectral evolution. What we do see in the X-ray spectra is a hardening with time, possibly linked to the emergence of a power law component, which was not there initially. NGC 5905 was also followed up in radio. This was the first one identified with Rosette. So we wanted to know whether possibly a peculiar blazar could hide at the nucleus of this H2 type galaxy, which could have done some giant flaring, which was unlikely given its optical spectrum, but nevertheless it was important to check. As we wondered, is a jet produced along with the accretion flare? No radio emission was detected 6 years after the X-ray peak. Now there's a number of ongoing searches for tidal disruption events in soft X-rays, one dedicated search based on the XMM Luton Sleuth survey in comparison with the existing ROSA database to identify new bright X-ray TDEs. Richard will talk about that. There's also a dedicated search in clusters of galaxies, which like Peter will talk about, and a search based on the XMM, the archival XMM database, and a few serendipitous detections have been reported. Just to show you one of the most recently published soft X-ray TDEs. It was detected with XMM by chance in a pointing. It was found in a search for highly variable X-ray sources in the XMM Newton database. It has a very soft spectrum of temperature about 0.1 keV, possibly subject to a fast-moving warm absorber. Fortunately, there only exists this one high-state data point. Further pointings, which by chance still included the source, only provided upper limits, so the X-rays declined strongly by at least a factor of 260. However, the fact that the peak luminosity is very high, just in the X-ray band itself, 5 × 10⁻43 ergs per second, and the ultra-soft spectrum, and the fact that this flare arose from within the central region of an inactive galaxy, so not an AGN, an inactive galaxy, make this another nice tidal disruption candidate. So here's a distribution of the peak luminosities of the X-ray detected TDEs, of the soft X-ray detected TDEs, and this is just the observed peaks and in the narrow 0.1 to 2 keV band. So these are safe lower limits to the actual volumetric luminosity observed. They range between on the order of 10⁻42 to a few times 10⁻44 ergs per second. Then just here shown, for example, for NGC 5905, these X-ray spectra were very soft, and we were very conservative in estimating the lowest possible seen luminosity, which is not allowing for any excess absorption in the host galaxy of the flare. If you add a bit of absorption, then you increase the intrinsic X-ray luminosity, and of course we did not catch these events exactly at the peak, and there has to be a volumetric correction, so typically the events might be more luminous by a factor of about 10. Now here's a summary of the published cases of TDEs or candidates as of early 2015. This includes all the sources which varied by at least a factor of 2 and up to, in the most extreme cases, around a factor of 10,000. And it includes those cases which have a host galaxy spectrum for assessment, that it is either a completely non-active galaxy, a quiescent galaxy, or that it is only mildly active. There's a number of, or at first the majority of events had been identified in X-rays. There's a number of UV events, and recently in particular a number of optical events have emerged. We've heard yesterday that the first event was a broad helium-2 emission line was 10 JH, but that there were previous detections which nobody knew about. So let me talk a little more about these events, which were first identified from the Sloan Digital Sky Survey in the optical. They were noticed for the very strong ion emission. They do have broad Balmer and helium lines too, but also a host of other emission lines. So if you first have a look at this spectrum shown in orange, this is the initial SDSS spectrum, which we noticed in the SDSS archive, searching very generally for peculiar emission line galaxies. And what is so remarkable about this SDSS spectrum is that the high ionization lines, like ion 10, ion 14, are almost as strong as oxygen-3 emission. So in terms of ion over oxygen ratio, this is one of the most extreme emitters in the SDSS database. And in particular, in order to see, simultaneous X-ray observations do not exist, but in order to see these highly ionized ions, which do have their ionization potentials in the soft X-ray regime, you need to have a strong X-ray continuum to produce these ions, which are necessary to create these lines. So we immediately checked the ROSA database whether there was an X-ray detection of the source, but there wasn't. Also there's strong helium-2 emission, broad helium-2 emission. There's broad Balmer, hydrogen Balmer lines with red asymmetric profile, and the helium-2 and Balmer lines also keep fading. We did follow-up observations with Spitzer, hoping that maybe in the mid-infrared we would see some high ionization lines too and could follow their evolution. None were detected, but with Spitzer we did see luminous mid-infrared emission. Follow-up observations with Chandra showed, however, that the source about 3 years after the SDSS high state was much fainter in X-rays. Now, when we noticed this system in the SDS archive, a few days later, we got a first follow-up optical spectrum, because the quick question was, are these high ionization lines permanent, or are they possibly transient and excited by a luminous flare? And now here you see the first follow-up spectrum, which was taken at the Qinglong 2-meter telescope. And as you can see, the emission lines faded. In particular, the highest ionization ion lines are completely gone. Have faded by more than a factor of 2 and 3 years. Now, what kind of galaxy is the host galaxy? Is this an active or non-active galaxy? We cannot tell with 100% certainty, because usually one of the major classification schemes uses optical emission lines because they vary. Any diagnostic classification comes with some uncertainty. Nevertheless, if we take the low ionization lines, put them in diagnostic diagrams, this is between LINA and H2 region. This is not a classical permanent AGN. So the X-rays are faint. There's no radio detection. In the optical low state spectrum, there's no evidence any longer for any faint optical power law emission. We just see the host galaxy. The iris galaxy, the iris colors indicate a relatively inactive galaxy. The black hole mass we could estimate from stellar velocity dispersion measurements, which is on the order of a few times 10 to the 6 solar masses. It's not completely gone. It's fainter. I'll show you. I'll show you in a second. So these observations imply that a luminous EUV to soft X-ray flare must have occurred. It was not observed directly because there was no simultaneous X-ray observations, but we do see about a factor of 2 variability in the NUV, near UV to near infrared continuum, and we see this broad and narrow emission lines. And now you see in much higher detail, actually I did not overplot the second spectrum, but the broad H alpha, it faints. It gets fainter by about a factor of 2. It's not completely gone in the first follow-up observations. So you see a zoom on the H alpha high state profile seen with SDSS. It's red asymmetric strong Balmer line. It has some extra peculiar narrow unresolved features which do not occur in any other emission lines. The same for H beta. So there's strong helium-2 in high state, which also fades. So we wondered, because there's no strong evidence for permanent AGN, did we see the emission line reprocessing from a tidal disruption event? illuminating the surrounding interstellar medium. So clearly this event must have occurred in a gas-rich galaxy, where the narrow lines come from the surrounding gas, where the broad lines might be linked in one way or another to the stellar material. However, I always worried, and I still wonder about all these optical transient emission lines. How safely can we really exclude a peculiar supernova? In this particular case, if all of this was due to supernova, it would be one of the most luminous known in several respects. In particular, these very strong iron coronal lines are very unusual. Just a few supernovae do have these lines detected, and this case is a factor of 100 to 10,000 more luminous than the few iron coronal line luminous supernovae. So we then carried out a more systematic search in the SDSS database to find more of these events. So the key criteria were to detect strong iron emission, iron coronal emission, and that the first follow-up optical spectroscopy showed that these lines were not permanent but faded. So we found 3 more good cases with fading iron lines, while oxygen seems to increase with time. All of them come from the very cores of their host galaxies. The host galaxies show H2 type emission line spectra, except for the high ionization component, and all of them are relatively low mass based from the fact that the absorption lines seen in the optical host spectra are no longer resolved with SDSS. So the overall similarity of their spectra suggests similar mechanism at work, and a very rough estimate based on the number of sources which were emission line galaxies which were looked at with SDSS. The rate is about this. So how much time do I have? Okay. So briefly, let me spend the last few minutes in addressing the question, what about tidal disruption events in active galaxies? So when we searched for the first events, it was very important that these happened in quiescent galaxies to make the point we actually see tidal disruption events rather than variability related to the accretion disk, which is permanently present in AGN, and so many AGN do vary in X-rays. Now, all the first cases I showed you identified in soft X-rays, they are quiescent, and the amplitude of variability, the drop in luminosity, is so high that it's much higher than observed in any known AGN. But again, now we can look at active galaxies and ask, do we detect tidal disruption events in active galaxies? How do they look like? How certain are we about their classification? And there's one very peculiar Cepheid galaxy called IC3599, which was first noticed in the Wizard All-Sky survey as one of the most variable AGN. It was first bright in X-rays, but then when followed up again a year later, it had faded by about a factor of 60 and continued to fade a little further. So at that time, a few outburst mechanisms were considered. In particular, that we had an extreme case of X-ray variability in a narrow-line Cepheid 1 galaxy, whatever the mechanism to drive it, possibly a TDE or perhaps some kind of accretion disk instability in this AGN. None of the possibilities were explored rigorously. All of them were mentioned. And at that time, in particular, when Martin Rees was asked about his comment about the system, whether it could be a TDE, he said he would like to see these events in quiescent non-active galaxies to be sure that we don't see anything related to a permanent accretion disk, which has some permanent luminosity outputs, which makes the AGN typical narrow lines. Now, interestingly, recently, IC3599 flared again with SWIFT. It was seen in other X-ray high state, which was at maximum almost as bright as the initial Wizard high state. Fortunately, we only noticed it a few years later and then did a number of follow-up SWIFT observations which showed that the source was then faint again. This is with SWIFT spectra in the optical UV and soft X-rays. You can see that also the optical and UV varies, but the highest amplitude of variability is seen in X-rays. We also found a Catalina optical All-Sky server light curve, which shows that the optical was bright already about 2 years earlier than the SWIFT X-ray and optical high state. And so what did happen in this galaxy? Well, the fact that it is a classical AGN, and in particular that the classical tidal disruption flares were not expected to flare again, then strongly points to variable AGN scenarios, possibly some kind of instability in the accretion disk. At least the amplitude is still quite high in comparison to other AGN, the amplitude of variability of a factor 100. However, we can now also consider variants of tidal disruption events which do predict repeat events. For instance, it has been predicted that the tidal disruption rate can be strongly boosted when you have a galaxy merger, or perhaps in the early phase of a recoil event. Optimistic predictions by Chen et al. Predicted the rate as high as about 1 event every 1 to 10 years. So maybe we are just seeing this. However, the host galaxy does not show any indications that it's ongoing, that we have an ongoing merger. Now, if we have a TDE in a binary supermassive black hole, the action of the binary temporarily interrupts the accretion stream on one of the black holes. So we have a light curve that does not smoothly decline, but that shows some quite erratic flaring. However, the second peak, 20 years after the first one, was as bright as the first one, and so this is an unlikely scenario. Campana et al. Recently, in application to I3599, suggested we might be seeing a tidal stripping event, and Ilya Mandel recently predicted, not explicitly in application to I3599, but as a general idea, that if you have a binary star in a single supermassive black hole, that might be disrupted and could produce a second flare. In that case, we don't expect a staggered peak. And just recently, we saw I3599 going into a third, possibly going into a third high state, where the optical is already as bright again as in the previous high states. So, in summary, soft X-ray TDEs have first been found with Rosat. They very well matched all the order of magnitude predictions from tidal disruption theory, and they are from quiescent galaxies and show very high amplitudes of variability. I didn't talk about Jeter TDEs first found with Swift. We'll hear about more of them later. Then emission line TDE candidates based on their broad and narrow emission lines were first identified from SDSS. And these were expected if a luminous accretion flare explores in a gas-rich environment. Okay, and there's some interesting future applications I put here. So thanks for your attention.
You showed us a slide a couple minutes ago with the IC3599 spectrum. It was on the screen for about 5 seconds. Can you show this to me?
Yes, yes.
There. We went that way. For the broadband spectrum.
Oops. Let me see. No. Yes. This one.
So these corona lines like macros, I think are very interesting. Actually, I've been observing the galaxies where we've seen the optical UV events, going back to them after a few years to see if maybe they developed these corona lines a few years after we saw the optical event. Is there a sense of where this gas is and what kind of time delays are expected between the TDE and this line?
I guess it depends on the the gaseous distribution in the environment of the core.
Right.
So it could typically be high density gas, say some parsec away. So yes, or closer. So so a few years. So the light travel along our line of sight might reach these clouds early, and then you have, with some light travel time delay, you reach further of this gas.
So it doesn't make sense a few years after
A few years, absolutely, yes, because of light travel time delays. You know, whenever the luminous flare reaches some say a molecular cloud, some dense gaseous material, you do expect some reprocessing and to see these lines.
Yeah, so in addition, building off that question, given the time scale observed in galaxies, is it conceivable that you could actually spatially resolve echoes or any object?
Yeah, so it would have been great to have better spectroscopic coverage. Let me see, the database we have is the first SDSS spectrum, but we only noticed it 3 years later than it was taken, because then it entered the archive. And so the first optical follow-up spectrum is 3 years later, and then we can see that there's strong changes where we do not have any reverberation mapping. And then we have another one another year later, and this trend is that the low ionization lines, the 3 gets a bit stronger, the highest ionization lines fade further. But the time sequence of the spectra is not enough to do reverberation mapping. However, it would be a great way. You know, there's this classical reverberation mapping in classical AGN of the broadline region. Now, these tile disruption events, you have an idealized situation of just one single giant flare, which then travels through the core of the host galaxy, and whenever it encounters some material, it's being reprocessed. So there's a lot of future potential.
I'm thinking less of reverberation mapping and more of like actual light echoes.
So the very, very closest subject, like, was over to 20 megaparsec, then after 10 years or so, it's like milliards. So it would be possible maybe that
Okay, you think of spatially resolving it directly. Yeah.
I guess you showed the Catalina Sky Survey. Did I understand right that was between two X-ray flares? And now the
Yes,
third flare is
yes, indeed. So this zooms now on the second flare. This is the Swift high state in X-rays, and the Swift UV high state with Catalina. You confirm that high state, but you show that it, at least in the optical, it has been on already earlier, about 2 years earlier. So this covers a time span of 2 years.
But we don't know what the X-ray may have been.
No, unfortunately not. We only have this Swift data
More
point.
recently you showed that it was coming up both.
Yes. Okay. Yeah. I was running out of time a bit, so let me just. So very interestingly, just recently in August this year, we saw that the optical was already bright again. The UV was a bit higher, but the X-rays were not yet. So unfortunately, then the source went into sun constraint. We could not follow it up further. But just last weekend, we had it was out of sun constraint. Immediately, Swift took a new observation, and the optical is still high, and the X-rays are still low. So if this is the onset of a new major flare, it means that the optical comes first. But we have to see how the light curve develops.
On the X-ray, there's an upper limit just before the second flare. Where was that chronologically relative to the optical problem data?
Let me just check. So the upper limit is, I think, from the XMM slew survey. And I think that was before the Catalina. Oops.
One more question and one more question. How much of a missing energy problem is there in the X-ray selected TV sample? You showed some photometric correct luminosity and it was pretty high. So I guess how trustworthy are those photometrics?
Volumetric corrections are uncertain. So the safest one, we have the measurement in the soft X-rays, and we can play a little bit with the absorption. You know, if you allow a bit of absorption in the host galaxy, not dramatic, but just what we see in our galaxy, because this very soft X-ray event, you boost it a little bit. But then in order to go to the volumetric correction, they can be a factor of a few, or they can be higher. So this is uncertain. We do not have any simultaneous UV observations of these first events to get the broadband SED.
Thank you.